Okay, good morning. All right, so what we're going to do today is we're going to go over, finish some of the questions on the sample questions I gave you. I also gave you, I just created an assignment with a few other sample questions because people asked me, can we have some more questions? So I just made up some more questions, okay? But let's continue talking about this. All right, just give me a second, let me find. So I think we did up to this, right? Up to 15. Yeah, let's see. Okay, let's get to question 16. All right, which, I think this only goes up to 27. You don't have to submit these. Okay, the first 15 I wanted you to submit, right? For last time. This one you don't have to submit. But let's work on it. So what's, yeah, maybe just shout out the answer. What, question 16 says, which of the following does UDP guarantee? And then, for example, like I mentioned to you, you know, both either on your test or on the final, you will have to explain your answer if you're asked to do so. Right? So which of the following does UDP guarantee? Sorry? Who said that? Yeah, why? Yeah, oh, I think last time it didn't, okay, I think, you know, that's right. I can't, okay. I think it doesn't save it. Yes, you're correct. But let me just check. I think this doesn't save it, right? Yeah, it's not going to save it. Yeah, so it's fine. Let's draw. Yeah, the point is that UDP is a placeholder for a transport layer that doesn't guarantee anything. Right? Remember, it does have a checksum, but that's about it. Yeah, so in this case, none of the above is correct. Okay, question 17 says, okay, so this is about network routing, and there's, here I say there's type A routing and type B routing, and later you have to choose what A and B are. It says in type A, each node constructs an array consisting of the costs to all of the other nodes and distributes that information to its neighbors. Type B constructs an array containing the cost using knowledge of the network topology. So which one is, what's A and what's B? So what is A describing? So what is, yeah, so what is this describing? And then what is this describing? Right? This was type A, and this is type B. So, yeah, I mean, there are 4 choices here. Which one is the best choice? Who said that? Benita, why? You said C, that's actually correct, but why? Can you explain? Sorry, can you repeat? Yeah. Okay. Yeah. Yeah, I mean, that's just the definition of the two. But let me throw a little wrench into your, this question. How do the nodes get to know the network topology? Is some oracle just tells them? So for the second one, for link state, how do the nodes know the network topology? Can you say it again? You broadcast what? It's table. So that sounds like distance vector then, right? So is it the same? So are link state and distance vector the same? Okay, then how do nodes figure out what's the correct topology if they get conflicting information? Route to where? Do you share routes? Yeah, okay, good. But thanks for being brave and speaking up. Yeah, so what about the rest of you? How do the nodes know the topology? Because in link state, we said that nodes know the topology. Well, how do they know it? Did anyone ever think about that? There's a central unit. Okay. Then couldn't that central unit just do all the processing and just tell the nodes the information that they need? Maybe we don't have to have the nodes run link state. Would that be a better structure if I had a central unit that could talk to all the nodes? Right? Yeah. So good. You're thinking. So I like that. Yeah. So you made an interesting, right? So you made an interesting claim that topology is different for every node. Yeah, yeah. So why couldn't the central node compute all spanning trees and just distribute it to the appropriate nodes? But why? If you have a central node, why not just have the central node do it? What? If what dies? Then you're an ISP or a telco. You buy a new central node, or you have a backup maybe. See, it turns out that engineering is not so different from law. Whatever you tell me, I can refute it and I can give you an argument. That's what you have to learn to do, actually. Right? That's what learning is. Right? Learning is about asking questions, about answering questions, about, if somebody says something, well, but what about this? Right? Like, to everything all of you said, I had an answer, right? That's what you have to learn to do. And again, there's no right or wrong. There's only like, well, okay, here are the assumptions I made, and here's what I can prove or do with those assumptions. If I want to do something different, I have to change my assumptions. Right? That's actually engineering. Engineering is not monolithic. It's not like one thing here. Okay? So we're back. Let's go back to that question. How do nodes need to know? So you guys have come upon some solutions, right? Obviously, so what's done here is there's no central node, typically, but there's no reason why you couldn't architect a network with a central node. You could do that. And that node could run Dijkstra for all the nodes and distribute it. There's nothing wrong with that. But typically, it doesn't work like that. Every node will run Dijkstra, will act as the central node and run. And, well, in that case, it needs to know the whole topology. And how does it get it? Well, there's a dissemination phase. I think that's what you were trying to describe. There's a topology dissemination phase before we run Dijkstra, right? Where nodes are going to basically, they're going to share the same, almost the same information that they shared in distance vector. They're going to share, okay, here are my neighbors. The assumption is a node knows its neighbors because it can talk to its neighbors. And it knows the cost to its neighbors. So that's what it's going to do. It's going to say, I have a link to, if I'm node A and BCD are my neighbors, I know that I have links to BCD, and here are the costs on those links. And then I'm going to send that out. I'm going to broadcast that out. So what you said was largely right. There's going to be a data dissemination phase, a broadcast phase where nodes are going to share information, and what they need to do is they need to construct the topology. Right now, the point I made about conflicting information and all is actually true. there could potentially be conflicting information there, right? If A and B are neighbors and A sends out some information and B sends out some information, hopefully A says B is my neighbor and here's the cost, and B says A is my neighbor and it gives the same cost. If they give conflicting costs, well, that's something that nodes have to decide how to reconcile. There's no magic. There's no magician that tells you what to do, right? So actually that data dissemination phase, which we glossed over, is actually quite important. Because without the topology, you can't run Dijkstra. So everybody good? All right, so so like I said, I wanted to throw a little wrench in there and ask what happens. How do you get this information? The information we didn't discuss, but yeah, it's done in a broadcast way, right? And it's done for a limited amount of time. There's no, as far as I know, there's no central node or there's no central mechanism that says, oh, now everybody has the topology. You do it for a certain amount of time, and just hope everybody has got the information that they need. All right, so let's move on. 18, explain TCP slow start. Like, what is the goal? How does it work? And then there's a second part that says how many packets are sent after 3 RTTs. So somebody want to explain what slow start is and what is its goal and how does it work? Evan, you know what slow start? Can you explain it?
Slow start
Yeah.
in the size of
Yeah.
the congestion window.
Yeah.
So every return trip, it increases the amount of packets in the congestion window, so more packets are
Yeah. How does it do it? How does it increase?
based on it increases by 1 with every acknowledgement. However, it grows exponentially. So after 3 return trips, it'll be 8 number of packets sent. So it's 2 to the n, where n is the number of return trips.
So it doubles it every round trip time.
Doubles it, yeah.
Yeah. Okay. But you mentioned something about it relieves congestion. Well, if it's doubling it, isn't that actually?
I don't think it relieves congestion.
How does it relieve?
Protocol where it deals with congestion.
How does slow start deal with congestion?
Because it builds up all the way
Yeah.
to the point where there's a congestion threshold.
Yeah. Yeah.
Slow start threshold from the last time.
Yeah.
5 nodes or a triple duplicate act, and then after it gets to that.
But you're describing TCP. So you're saying maybe TCP deals with congestion.
Yes.
But I think slow start doesn't necessarily.
The TCP slow start.
Yeah, but we're specifically talking about slow start, yeah.
Yeah, slow start doesn't deal with congestion.
Yeah.
It builds up.
Yeah, so, but what's the purpose of slow start? Why are we doing exponential increase? Do you know, or do you have an idea of why?
Exponential increase because you would want to maximize the throughput.
Yeah, okay. Yeah, I mean, the point is that, like, for example, when you first start, you have no idea what the state of the network is. And if you, let's say, are too conservative, it might take you a very long time to get to the congestion boundary. So slow start does that, tries to get to the congestion boundary very fast. So actually, paradoxically, you're trying to break the network as fast as you can. Okay? So that you learn about the network, and then you can start to do the other things that TCP does. So the point is you should be able to articulate, right? You should be able to have your own feeling for what is, slow start, but all these mechanisms. You should be able to articulate, right? So, I mean, this ability to articulate is actually what explain briefly means, right? When I say briefly explain, I want you to think a bit and then write down something. Don't give me a data dump, right? Write down everything you know about a subject in hopes that something in there is right. because that doesn't show understanding, right? So this is very different from what maybe you used to do in the past. Okay? Okay, so someone else, how many packets are sent after, let's say, three RTTs? What? Okay, Benita, you say 15. Why? Can you explain how you got the 15? Yeah. Good. So you would make that assumption, right? Exactly. Right. So let's say something. So after 0 RTT, right? What's your congestion window? 1, right? Then after 1 RTT, right? What's your congestion window? 2. After 2 RTT, your congestion window is 4. And after 3 RTT, your congestion window is 8, right? And I think what Evan was saying, after K RTT, your congestion window would be 2 to the K, right? Yeah, but here I'm saying after 3 RTT, right, you're going to send this. You add this up, you get 15. Okay? So, all right, so that's pretty straightforward. Yeah. Yeah. I mean, in the beginning, you're going to set your congestion window to 1 and transmit that. Yeah. 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 So you're questioning why I'm counting the 8. Well, yeah, I mean, I guess maybe this is a matter of interpretation, yeah. I mean, I'm just saying after three RTTs, my congestion window goes to 8, and I'm going to send those packets. I'm going to transmit those packets, right? So I said, how many packets are sent, are transmitted? Yeah. But, yeah, I mean, if you want to, I think your interpretation is defensible, right? As long as you're clear about it. See, what's not acceptable is, okay, so I have kids in the local schools, okay? And, those of you who went through the local school system, you think back to primary school. How, think about a math question and think about what you wrote for a math question. You just wrote numbers, right? Right? Like 10 divided by 2 equals 5, 5 times 3 equals 15. That's what you did, right? Do you guys remember or not? Like, but you went to the local school system? Back to school. You just had to write numbers down, right? And then in the end, they looked at your final answer. Right? Your working wasn't really working. It was just numbers. And that irritated the heck out of me. Like, I would see my daughter or my son do this. I'd be like, what? Just numbers. Like, no explanation. Yeah. So you cannot just, if you just wrote down the answer and didn't explain yourself, I wouldn't give you credit for it. But if you wrote and said, this is what I'm doing and why I'm doing it, yeah, I'll give you credit for it. You see the difference? That's why I said your position is defensible. But your position is not defensible if all you write down is 1 plus 2 plus 4. Yeah, so I hope everybody understands that. The compromise here is I'm willing to be flexible, but you have to explain yourself to show you understand what's going on. Yeah. I mean, I don't want to say that. It depends. In this situation, maybe yes, because both are defensible. But if it's a situation where it's not so defensible, but I can almost understand why you might think that, I'll give you partial credit. Yeah, Evan.
The answer would be 7.
It'd be 7, yeah. Correct. It'd be 7, sorry. Yeah. Okay, everybody good? Okay? Again, I'm hoping you don't just learn about networking here. You learn a little bit about learning, right? And something you can take away with you to help you in your other classes as well. Okay, 18 done, right? So 19. Okay, so I think this is just an explanation. So the 32-bit, so IP addresses are 32-bit. We talked about CIDR. Consider this address here. Let me not. So consider this address here. Okay, let's start. Explain what the /24 means. Can you tell me what the /24 means? Last time I asked you and you had it backwards, right? Was that you? Okay, anyway, what does /24 mean? Sorry, number of what? Number of bits in the subnet. Yeah, that's right. So what's the rest of the? Yeah, correct. So how many addresses and how many hosts? So this is the subnet part, right? Right, and then so if you have 32 bits, there's a subnet part and a host part. Okay, so how many IP addresses are on this subnet, are in this subnet? Right, 2 to the 8, which happens to be what? 256, right? And how many hosts can this subnet support? Yeah, 2 to the 8 minus 2. Because all zeros and all ones we don't assign. Okay. Okay, so question 20. So let's look at this address. And maybe you guys can just maybe take a couple of minutes and do this. Okay, so yeah, so let's do it. So there are 4 questions here. Can everybody just do it? Like take a few minutes and do it. Just make sure that you know how to do it. If there are any questions, now's a good time to ask. So can somebody help me? So we should be able to at least have started the first part. So how are we going to start the first part? What's the first valid host IP address in this range? So, okay, so let's call this, I realize I may want some more space. Why don't we do this? Okay. Okay, so yes, Benita, what did you say? .2068 point what? Okay. Okay. So how did you get this? Right. So you're saying there's 21 bits in the subnet part, right? So let's walk through this. Hopefully everybody is following along. If you're not, just raise your hand and say, I don't understand. Okay, so there's 21 bits in the subnet, which means how many bits in the host? Yeah, so what is that? Yeah, 11, okay? Right, so the broad idea is there's 21 bits in the subnet. Those remain fixed. Then there's 11 other bits. And if I want the first valid IP address, what am I going to do with those 11 bits? Yeah, so maybe I want to be a bit more precise, or if you look carefully, first valid host IP address. Yeah, so I'm going to set it to 1. So I'm going to set it to 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. So, and, right, so you have the first 21 bits, the next, the next 10 bits are all 0, and the last bit is a 1. And that is the valid IP address of the first host. Okay? Everybody get it? Okay? And that turns out to be 206.68.144.1. So what Benita was saying is that since the subnet ID is 21, you don't need to worry about the first 16 bits. They're going to remain the same. Right? They're going to stay as 206.68. It's a third byte that you're going to have to dissect into 3, take the first 3 bits, keep them fixed, and zero out the next, I think first, no, hang on. The first 5 bits, fix it, and zero out the next 3 bits. Okay, and that's how you get 144. And then the last one is all zeros and a 1. Right, because we want a 1, right? We want the first valid IP address is a 1. Okay, is anybody have any doubt about this? Okay, so that's easy. Okay, so maybe it's worth writing out here. I have written out here, but I didn't. So let's see. So actually, 206 doesn't matter, right? 206.68 doesn't matter. Then that third byte will be. If I just write out 149, what you get is 010000100. No, I picked the wrong one. Hang on. It is the third byte. 110010101. Right? Yeah. So, by the way, like this 103 doesn't matter actually, right? Because the subnet ID, subnet part is 21 bits. So the subnet part is going to be these 16 bits plus these 5 bits. Okay? And that's what we're going to fix. Okay? And if you and then if you convert this to binary, you will get 206. Yeah. So when you zero this out and you just look at these first 5 bits, that's 144. Okay? And that's where the 144 comes from. But I did this because so this is actually, maybe it's worth putting this first. Oops. Okay. So that's how we get that. Okay? So then now it's asking us, what is the broadcast address? How are we going to compute what is the broadcast address? What's the broadcast address? How do we compute that? Set what to ones? Yeah. Who said that? Yeah, correct. And then this one is going to be right? And this is then going to be what? Yeah, correct. So this is the broadcast address. Okay, so what's the last valid address? Well, okay, I mean, it's just going to be the one. It just be that, right? It just be the one right before the broadcast address. Okay, and then what is the subnet mask? So maybe I want it in. Yeah, in dotted decimal. So what is the subnet mask? So we know that the subnet part is 21 bits, but if you look at the TCP/IP settings in Windows, you actually don't see like 21 or whatever. You see what looks like a dotted decimal IP address. Yeah, so what is that? I'll give you a hint. It's related to the 21. No. So maybe explain how you would do it. Explain how you get it. And the rest? Yeah. Okay. So what we would do is you take this. Now, the first 21 bits are 1 to indicate they're part of the subnet part. So this is going to be what? So what is this first part, Benita? Now for this one, I'm going to set this to 1, and then set all this to 0, right? So what did it end up being, Benita? 255.255 dot what? 248.0. Okay, so this is the subnet mask. So this is an equivalent way of telling you /0. /21. Right? You see, it's equivalent to that. Okay? I mean, most of the time we see like the slash, but there are still protocols or specs that use this. The reason this is called the subnet mask, right, is you can use it to extract the subnet ID, right? By just doing what? What logical operation do you have to do to get it? What? Yeah, you could just do bitwise AND. Okay? So if you take an IP address and you AND it with the subnet mask, it gives you the subnet ID. Okay, okay, good. So we have the answer to this. That's not that one, sorry. Oh, then in binary, it would just be convert everything to binary, right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 5. That's a subnet mask in binary. Yeah. Yeah, because the all 0 is not assigned to a host. Yeah, and I mean, I asked what's the first valid host IP address? Yeah, so that means there's a machine on the network with that address. It's a convention. Yeah, the convention is not to assign the all 0. Yeah, but you ask a good question, you could. Because it's not used anywhere, right? The all 0s, now the all 1s has a functional use. It's for broadcast. The all 0 doesn't have a functional use. So you could. But like I said, the convention is to not assign it. Yeah, so let's go with that convention. But as I said, if you were designing a network, you could. Right? If you're building your own protocol and you want to be efficient and get that one extra host IP address, go crazy. Yeah. Okay, good. Like that's what I want people to do, to ask questions and think beyond what is. Think about what could be. And sometimes you'll find out you can't. Like if you want to have the broadcast functionality, you cannot assign the all ones to a host, right? Okay, any other questions? Okay, this is done. Okay, let's skip this for now. The reason is I told you I'm asking you to do some assignment, and this is actually on the assignment. I realize it's the same question in disguise. So this is quite simple. So we'll skip this for now. You just do it on the assignment. But let's do this one. This one's interesting. Okay, so here is a network. And I want you to assign, for all interfaces, assign IP and MAC addresses. And then, so that's task one. So that's one here. And then, this is like, and so this is a picture of a NAT, right? So this here is a NAT router. I think this is the same picture I used in the notes. Okay, so this is a NAT router, and then I'm just asking you a question. Suppose that one of the clients sends an HTTP request as follows, and I want you to fill out the NAT table. Okay, fill in the NAT table after that request has been forwarded. Okay, so yeah, please do it. So let's look at number one. Assign IP and MAC addresses to all nodes in this network. So how would you, let's start with the easy one. IP addresses are easy, right? To hand out. So how would you hand out IP addresses here? .2.0. Yeah, so this tells you, so this piece of information here gives you a lot of information about your network, right? It's telling you what the subnet ID is. The subnet ID is 10.2.0. Okay? So that means all of your nodes in the network on the private side should have, the first 24 bits should be 10.2.0. Right? So, and you said we can assign it to be anything. Like I could make this 10, right? And then 10.2.0.9, 10.2.0.8. Right? Is that it? No, it's not it. So what's missing, Evan? Right. Okay? Okay, so IP address easy, and we had, okay, so now the hard one. MAC addresses. So I mean, there are four interfaces, so we have to assign each interface a MAC address. So how are we going to do that? Anyone? Did you guys here come up with something? Are you guys discussing this? What? Something else? No, it's okay. It's okay. No, I thought you were discussing this. You were trying to figure this out. But how would you assign MAC addresses here? You know? You just came in, I know, but you can catch up. Well, I mean, I'm asking you to assign it, so just assign it. Sorry? Do you guys ever hear about this story about this? Yeah, okay. I'll come back to you in a minute. I just want to address why everyone is so silent, and it reminds me of a story. There's a story about this. It's kind of like one of these urban legends, but I think it's actually true. It's about this guy called George Danzig. He's a computer scientist. He's a famous computer scientist, but he wasn't born famous, right? So he was not famous for a long time. He was in school, he was in college, and he tended to be late to things. And so he got to class late one day, and he kind of missed class. But he knew the professor had a habit of putting homework on the board. So he saw some questions on the board, and he figured that's homework, right? So he wrote it down, and he went home and he worked on it. He's studious. He's late, but he's studious. So he worked on this, and he said, "Man, this homework's really hard. I regret missing class." And then he worked on it, and he finally turned it in his homework like the next class, and he's like, "Professor, this was a very hard homework." Professor chuckled, took it, right, and didn't do anything. And weeks later, I guess George had submitted something, so the professor was looking at it going, "Oh my God." What he put up on the board was not the homework. It was unsolved problems in graph theory, right? In computer science graph theory, George Danzig had solved them. When so my point is that no one told him they were hard or unsolved. Just because I told you, let's do the hard problem now about MAC addresses, all of you are like, "Oh no, it's hard." Actually, the MAC address is the easy part because there's no constraints. Like you said, you could assign them to be anything, right? Framing. Don't get trapped by framing. Somebody tells you it's hard, okay, take that as a data point. It's for you to decide, it's for you to think, put on your thinking hats and figure stuff out, okay? Is that why all of you were so quiet? Because I said it's hard? Why didn't you guys speak up in the back? Yeah. You two are usually very vocal. What? Yeah. No, it's like I told you. I think I told you this before. If I'm pointing at someone and you feel the need to look behind you, you're the person I'm talking to. Yeah, so why didn't you speak? I'm just curious. Okay, it's fine. No, I don't want to put you on the spot. But yeah, you can assign anything here, right? For example, we could let this one be. But the key is in the current set of protocols, how many bits is the IP address? Is the MAC address? You said just assign 1, 2, 3, 4, but actually you have to assign how many bits? 48 bits, right? So I could be, for example, AA, BB, CC, DD. Is that it? No. I have to have 6 of these, right? Yeah. And then if I wanted to do 1, I could do right? I mean, yeah. The point is, yeah, there's nothing, and I think as one of your classmates said, it's burned in by the manufacturer. But because it's a field in a network packet, you can spoof it. So there's nothing that says you can't spoof the MAC address. So if a DSCP router is doing MAC address filtering, if you knew what it was, you could spoof it. Yeah, just because it's burned in by the manufacturer doesn't mean that you're out of luck. Okay, so that's it. So you can assign anything here. Yeah, I mean. That's it too. Okay, and so on. Okay, and then let's just do the first part of this, where you have this node. So let's say that one of our nodes, so let's say this guy is the one that sends a packet, the topmost client. So how would you fill out this NAT table? So can somebody help me? Yeah. That's right. Correct. Yeah. Okay. So what port number do you want to put here? Like, give me something. Okay. Mm-hmm. Yeah, exactly. Right? So the 7,000 is that the web browser is running on port 7,000 because the packet came from there. And 7001 says, okay, I'm going to masquerade as some other port number. Now, typically, like, yeah, you have to choose large port numbers. The smaller port numbers are reserved by the system for system use. The port numbers can be the same, yeah. There's nothing that, but they cannot be the same on the same host. Yeah, but here they can be different, yeah. Okay, that was 22. Okay, I think we've done this so many times. This should be quite easy, right? Okay, here. So suppose, so there's y and x here. Suppose y equals 2. And for what values of x will Dijkstra's algorithm work and not work? So how would we do this? First explain. Don't give me an answer. How would you do it? Hang on. What did I do here? Oh, I changed the number, so I can't use this solution. Okay, let's figure it out. So so here Dijkstra is going to choose what? Well, yeah, so Dijkstra will choose this. Okay. Then the next thing that Dijkstra will choose is this, right? Right now, depending on what x is, he's going to choose either link 2.3 or link 4.3, right? So what do we have to compare? We have to compare 3. Hang on. No, but 1, 2, 3 is 3. Right? You always compute distances from the source. So in the second step, it's actually going to choose link 1.4. Because link 1.4 has cost 2, but link 1, 2, 3, if you add 2, 3, then you route from 1. Does that make sense? So Dijkstra is, when you're doing your comparisons, you're always computing distances from the source. Okay, so there's one, it's cost 3. So you're always going to choose 2. Yeah, I'm correct. Yeah, the example I had is different actually, but let's stick with this. In this case, it will always work. Correct, because at this point, this is what I'm going to do, and at this point, I can see all negative edges. You remember I told you before, when all of the negative edges are incident on the source, that actually will work. But actually, that principle applies anywhere. If I ever get to a node and I haven't seen any negative edges, and now I can see all negative edges, that actually will still work. Because I can make the choice. Right here, at node 2, if x happens to be negative, I'll choose it properly. Right? I think that's what you're saying, Evan. It will work. There's no chance that after I make a decision, in the future, a negative edge will come up. Because here I have no choice. The two edges I've highlighted are the two that will get selected. Does that make sense? Okay, so yeah, exactly. So let's do this. So for this case, Dijkstra will always work. Okay, so good. But let's do this. Let's come up with an example where Dijkstra will not work. And that's what Evan was trying to do. So let's do that. 1, 2, 3, and 4. And you said I make this 4, right? Yeah. So now we can compare something. The reason is, so now Dijkstra is going to choose this, right? So what's the next thing that Dijkstra is going to choose? So in the second step, what will Dijkstra choose? Which edge? Why 2, 3? Yeah, because this 3 is less than 4. Now we had another choice, right? There was another choice that we could have made, and that choice has an unknown in it that could be negative, right? So how would you figure that out here? So you would do, so this cost is 3, right? The top is 3, and the other is 4 plus x. So when is Dijkstra correct? No, so when is Dijkstra correct? So on the left I have 3, on the right I have 4 plus x. So when is Dijkstra correct? No, I know, you're doing algebra. Don't do algebra. Yes, exactly. And now we can do algebra. But this is networking. What you did is algebra. And I'm okay with it. But don't do algebra in your head and just write x less than 1. You could have copied that, right? Yeah, no, that's what I always tell my son as he's doing this stuff. He's like, no, my teacher says I don't need to explain. I said, I don't care what your teacher says. You have to think about the real world. Like in the real world, you have to explain yourself. Okay, so that's, and then you can just solve for x. Right, so go do some algebra for me. What is x here? Yeah. So this is when Dijkstra will work. Okay? Yeah, sorry, my example was really bad. Okay, how about this? So this was just another example. Okay? We did this already. Dijkstra will always work here. Now, how about here? So I said 1, 2, 3, 4. And I want to do, I don't know, I haven't solved this, so let's solve it now. 1, 2, x is 2, this is y. So for what values will that actually work and not work? It will always work. Because, again, the y is incident on the source. Yeah, so again, yeah, this is the danger of changing numbers quickly. I actually, in my original problem, y was 4. Like if you look at my original, like what I'm referring to, I have x to be, y to be 4. Yeah. Yeah, so that's a good question. Probably in the real world, you're not going to encounter that. Yeah, but I guess just to be complete, so we understand when Dijkstra works and when it doesn't. Actually, it turns out there are other algorithms that work with negative edges that also have polynomial running time. Yeah, but again, this is not an algorithms class. Okay, good? Okay, that's 22, 23. Okay, 24. Talks about distance vector. Okay, the fundamental reason for which loops form in the distance vector protocol is that some node A decides to use some neighbor B as the next hop based on routing information that was propagated by A itself. And give an example of this, and yeah, so that is, can you give a simple example of this problem with distance vector? So can somebody try? There's a very simple example, right? Yeah, Evan? Yeah, that could potentially work. So, yeah. So no, and then what are you going to do? You're going to have one of these links break, right, or something? Yeah. So it turns out actually in this case they won't. And you can almost see why they won't, because if one of the links breaks, you still have a connected graph, meaning that there exists a route to every other node. It will take a long time, but it will not count to infinity, meaning that it will eventually stabilize. And that's what we saw in class, right? It took a long time. Yeah, but you're not going to get a routing loop. But there's a routing loop for a while it's stabilizing. So it's bad in terms of convergence. So that's good. So this is an example of where this is bad news, travel slowly. But how about if you wanted to see, so this would actually satisfy this question. But actually, I was really thinking, can you show me where it's catastrophic?
So if you make another just from C to D.
Yeah, exactly. Yeah, if you do this, and now the link CD breaks, then pre-change, everybody thinks they have a route to D. That route happens to be through C, but A, B, C all have routes to D, and they tell each other, we all have routes to D. So when C's links breaks, C will use either A's or B's link to D, or it thinks it can. And that's the problem. That's the routing loop, because A and B are using C. So do you guys see the routing loop? And that's the cause. So, and actually, the simplest example is just this. Yeah, and just one of these links breaks. Yeah, so it's even apparent in this example here. Okay, if one of these links breaks, then the node that wants a route to the node that's no longer connected thinks its neighbor has a route to it, and they will just ping pong back and forth forever. And the problem is, in both these cases, there's no further route to D. right? If there was another route, you could recover. Take a long time, but you would recover. Yeah. Yeah, I mean, that's your assumption, right? I mean, if you want to state, I said yeah. I mean, I didn't ask you to assume that, but yeah, if you want to assume it, then yeah. But you could actually come up with an example, and I think we did in class, where poison reverse will not work. It will still result in a routing loop. The one on the right, yeah. Correct. Yeah. I mean, what will happen to the example on the left if there's poison reverse? Yeah. Yeah, I mean, it stops the routing loop, but it also means you can't route to C. But that's okay, right? That's fine. I mean, it's fundamentally that link broke. The ground truth is that there's no more route to C. And if the network, if the protocol concludes that, you're okay. Yeah. But you're right. The one on the right, poison reverse, will not work, depending on the edge costs. Right? It will choose one of them. That guy will lie, but it could still choose the other route. Right? The idea being that if this link breaks, and let's say A is actually using C, but B is using A, right? Then A using C will prevent C from using A, but it doesn't prevent C from using B, because B will lie to A, but B will not lie to C. There's no need. Right? Everybody see that poison reverse will not fix that. Okay, great. Okay, let's look at 25. If TCP provides reliable in-order delivery, why would you want to use UDP? And then give application where you'd be better off using UDP, give application you'd be better off using TCP. So, can somebody tell me? How about you guys in the back, the back row? Yeah, tell me. They don't care about what? Okay, yeah. Yeah, so for example, you said something, if you want maybe less overhead, right? And what else? So the question is, when would you want to use UDP? When you want less overhead? When you what? When you said what? Don't care? Okay, don't care about missing data, right? Right? Maybe you want better control over timing. Remember, TCP has timing issues. Okay? So give an application that might be better off using UDP. You were giving me an example, what? Yeah, okay, so something like Zoom, or maybe more generally, things that are that depend on real time. And how about for TCP? What application is better off using TCP? Huh? Email. Okay, yeah, that's fair. Maybe e-commerce, right? Some bank stuff, right? You want the reliability there. Okay. Again, these are just to get you thinking about things, okay? And like I said, being able to articulate in your own words things. Yeah, timing. So maybe timing is part of that. So you want control over time, but I think that's fair, Evan. So when you want faster processing, yeah, because it's not just faster in terms of timing. There's less processing because you don't have to compute all the things that TCP does. Okay. Okay, give an example of what I want to say. A simple network in which link state routing returns a different path from distance vector. Okay, so yeah, mix the two. The simple here is key. Don't try to construct a very large network. Sorry? You can do anything you want, yes. So example of a simple network which link state returns something different from distance vector. So anybody want to take a stab at it? Yeah, how about, again, last row, but these other two folks here. Yeah, so give me the example. Tell me. Okay, I have A. Maybe just tell me A is connected to B. Okay. Okay. Negative what? Okay. This. Okay. Yeah. So explain. Okay. So what the extra here? Correct. Yeah. So can I change color? Let me see. Yes. Okay. Okay. Then. So this is link state, right? Okay. What will distance vector do? So what will distance vector find? So the problem is the route to what? To C? So from A to C, right? So if we look at the route from A to C, from distance vector, from link state, we get it's 2. But what's the true cost? It's -5, right? So why will distance vector give a different answer? No, so that's link state, but why will distance vector work? Yeah, so when A starts, in the first iteration of distance vector, what will A do? It will say its route to C has cost what? 2. Right, correct. Then what will happen? It will learn, what will it learn? Yeah. And remember what nodes do in distance vector is they run Bellman-Ford, right? A is going to say, I can go to C directly, or I can go to C through my neighbor B. And it's going to say, it's going to do the exact computation. My cost to B is 5, plus my neighbor's cost to C is minus 10, so do 5 minus 10, I'll compare that to 2. So yeah, exactly. So this is vector will correct. So this is a good example. Okay? Yeah, so in this case, so red is Dijkstra, and this one will eventually give you this. Yeah, but it will take a couple of iterations, right? We start off by taking a direct route when it doesn't know anything. Yes. Thank you. Good, great example. Okay, everybody good? Okay, let's move on. Last question. Okay, assuming that the available link capacity and receiver window are infinite. Okay, so I have a router with a outgoing link that's infinite, and I have a receiver that has there's no flow control. Okay, so that's what I mean by receiver window is infinite. The advertised window by the receiver is infinite. How many round trip times does it take for TCP to send the first 10 packets? Let me see what I'm trying to assume here. Yeah, so this is at the, so I'm just starting up a connection, right? So actually we've done this already. We did this before, so I think this is a kind of a repeat, or it's a close, it's almost a repeat question. So I'm not asking you how many packets did you send in so many RTTs. I'm not asking you how many packets to send, how many RTTs to send a certain number of packets. Yeah, that's actually what I was looking at. It's at the beginning of a connection, so yes. So, but again, if it's not stated and you want to make that assumption, just state it, right? So it's important that you don't just start computing and giving me numbers. You have to say, I'm going to assume that the connection, uses slow start, and that's why I'm doing this computation, right? That's an explanation. Giving me numbers is not an explanation. Okay? Yeah, then you can make that assumption, yeah.
Also, I think the last question we did assume this we did, but what if there have to be a return trip for this thing?
Oh, you're assuming, you're, no, but there's RTT, right? The RTT is there.
Yes, that wouldn't that be a full RTT of no data?
Oh, you're talking about the handshake?
Yeah.
Yeah. So that's a good point, right? So you can say, I'm going to assume that, yeah, correct, yes. Yeah, I'm assuming here that we've already set up the connection. You're absolutely right. In fact, I missed that out. But you're correct. There would be, yeah, I mean, there's like 1 to 2 RTT there. It might be actually 2, right? Is it?
It's one with the three-way handshake, the second one.
Yeah.
They send data and the second acknowledgement.
Yeah, they could do that, yeah. Okay, good. So, yeah, so you can assume that the handshake is set up. If not, you can add that 1. Correct. Yeah, so let's say we assume, so start, and we say the handshake is already set up. Okay? So then, how long does it take to send 10 packets? Yeah. So let me see. So what did we do before? We did 1 plus 2 plus 4. This was 2 RTT, right? And then we get 8, right? And that gives us 15, which is more than 10. So why would you need 4 RTT? Yeah. Okay. So again, make sure you state your assumptions. But here, we're talking about just sending, right? So just like we were discussing before, in 3 RTTs, I can send 15, right? So to send 10, I still need 3 RTTs, right? And I think you can figure out for the K, you have to be a little bit, I mean, you basically have to do what? 1 plus 2. So this is like 2 to the 1. This is like 2 to the 0 plus 2 to the 1 plus 2 squared plus. So I want to send. So after M. So. So this is going to be M RTTs, okay? This is going to be less than K. K is the first packet. And then you need to do some, like, I can share with you what answer I got. So you work this out. Ceiling of log 2 of K plus 1 minus 1. Okay? I'll make that bigger. Again, this is just housekeeping. But the idea is you want to add up the total number, and you want that to be less than K, right? And then you just kind of solve for this. You can do some. I did a bit of messy algebra. Okay, so somebody can check me on this. If you have any questions, you can just post it to Piazza. Sorry? Yeah, correct. It's a geometric progression. Yeah. Now, if you're doing this in AIMD, in AIMD we would do 1 plus 2 plus 3 plus 4, right? You also know what kind of progression that is, right? Right? So what's 1 plus 2 plus ... up to, let's say, K? Yeah, I hope, so you can do it. Or there's actually a closed form expression for that. In this case, it's K times K minus 1, or K times K plus 1. Hang on, so 1 to K, right? So I have to do this in my head. I don't remember my stuff. So let's assume K is even. If K is even, right, then it's K plus 1. It's K times K plus 1 over 2. Yeah, and it turns out that also works for K odd. But for even, you guys can see it, right? You can. There's this story about so there's a mathematician called Gauss, and there's a story about Gauss that, so he was quite precocious, and in class, the teacher tried to keep everybody, Gauss always had the answer, so the teacher wanted to keep him busy. So he said, add up 1 to 100. Again, this could be an urban legend, but this is a story that I heard. And so the teacher thought this would keep Gauss busy. And it didn't. Because Gauss was a bit smart, and he said, okay, what we can do is we can start to pair up numbers. Okay, so in this case, if you pair up the first and last, it's 101. If you pair up the second and second to last, it's also 101. Because there are 100 numbers and you're pairing them up, there's 50 of them. Yeah, so that's the answer. Yeah. Okay, so you should, and this is what you would need to kind of add up if you're adding up during the AIMD phase, right? If there are no losses, right? Because what we're doing is we're increasing the congestion window by 1 every RTT. Okay, as opposed to slow start where you're adding up this things that's growing exponentially. Okay? Okay, let us stop this and yeah. Yeah. Okay, so tell me why, if you just have A, B, and C, so this is a good question. Tell me why it causes count to infinity. Oh, this is the example in the notes, right? Yeah. Um, yeah. I'm trying to understand what you said. Yeah. 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 Yes, excellent. Thank you so much. I love it that you just answered the question and you thought faster than me. So I like that. You get it? What will happen is eventually, as they're ping-ponging back and forth, at some point, A's cost to B through C will be greater than 50, and C will just use its own route. Yeah, this is, again, bad news travels slowly. Yeah, exactly. Good. Okay, cool. But thank you for asking. I like that. These are the kind of things that you have to ask. And I really like it that you ask in class because, well, to me, it gives other people a chance to answer and show and reinforce. And I think other people also can see that it's okay to have doubts. Okay, just you can work through them. Okay, good, thank you. Anybody else? Okay, what I want to do now is if you go to Canvas, again, just a couple more questions, and I'm giving you till the end of the day to do it. What do I want? Hang on. Yeah, just go and start the assignment. This assignment for today. But as I mentioned, I've given you till the end of the day to do it. Okay, so the questions look like this. Just a couple of questions. Yeah, I mentioned to you, right, the CIDR aggregation, I realize is the same, almost the same. So just do it here. Okay, it's not very difficult. And then just a couple of other questions. Okay, so for you to do, and yeah, just submit by end of today. Okay? I think it's until 23:59. Let me just double check. Yeah, 23:59 today. Okay, cool. Okay, so I think we can end class. If people have questions, I can be up here for a bit. Thanks. Oh, and you got my notice about the quiz on Wednesday, right? We're in LT6. Okay, and try to come a little bit earlier so we can just get everybody settled. And I apologize, like if you have class afterwards, if for that Wednesday class, if you could just let your follow-on class know, you'll be a bit late because you have a graded assessment. I want to give you from 1 to 2. Okay, the full 1 hour. All right, so again, if you really have an issue with the follow-on class, come and see me. Okay, we try to work something out. But if you can, for that one session, just let your follow-on class know. Okay, thanks.